welcome to today's colloquium. And today we are very happy to have Feryal Özel from Georgia Tech to give us a talk on black holes and event horizon telescope. And usually it should be a person that in this field to introduce the speaker, but as you know, I work on nuclear particle physics. But since Özel used to work on particle physics, so I feel a bit safer to introduce them. And I also have some experience in astrophysics. So when I was a junior, I actually work on a strong gravitational lensing from black holes. So yeah, so it's pretty much related. Before Misty sent me an email like requesting to inviting you, I was with a similar ideas of having a talk on black holes also. And then, but maybe before we start, let me briefly introduce Feryal. So she got her PhD from Harvard in 2002. After that, if I get it correctly, you were a Harvard Fellow at IIS Princeton. And then since then you work at University of Arizona. And then very recently, last year, she joined Georgia Tech and then taken the position of the chair of the physics department. And there are a lot of I saw your a CD, and there are a lot of awards you have won, and I just name a few. So she was awarded the Maria Goldberg Mayer Award in 2013. And in case you don't know, Maria was the second female physicist who won the Physics Nobel Prize on the nuclear fuel model. And in 2020, Feryal also won a Breakthrough Prize. And so she's an expert on neutron stars, black holes, and magnetons. And today she's going to introduce her research to us and then give us an update on event horizon telescope. Thank you.
All right. Well, thank you so much for the invitation and that introduction. It's really, really nice to, come down the street and visit our sister institution and get to meet a lot of you today. I've had many nice conversations. And in this hour, I would like to tell you a little bit about the work that we've been doing with the Event Horizon Telescope on imaging black holes. But I figured, this was the first image on the right of the black hole in the M87 galaxy that we shared in 2019. On the left, the image of the black hole at the center of our galaxy, Sagittarius A star, that we shared in 2022. I figured you've seen the images, so I kind of made a slightly new talk for you on, okay, we've seen the images. Now what? What did we learn from it? This is a physics and astronomy group combined together. I want to tell you a little bit about what physics we learned and what physics we uncovered that we don't know, and where do we go next. So my talk is going to be a lot more on the theoretical and computational side of understanding black holes based on these data than on how we gather the data. So having said that, let me, of course, introduce you to how we gathered the data, the telescope array itself that we call the Event Horizon Telescope. It's a bit of a misnomer. It's not a single telescope. In fact, we didn't build any telescopes for this experiment. This is an array of telescopes, radio telescopes, that are capable of observing in the millimeter wavelengths around the globe. And here is the telescope array as it stood in 2018. It keeps on evolving. We add new stations, existing telescopes that are equipped with what I will describe as very long baseline interferometry capabilities and millimeter wavelength observing capabilities. And it really is it spans the globe from Hawaii to Arizona to Mexico to Greenland telescope is our northernmost point. South Pole telescope is our southernmost point. Two telescopes, which themselves are arrays in Chile, in the Atacama Desert, and in Europe, the IRAM telescope in Europe. And what are all these telescopes doing? Well, they're participating in an observing technique called very long baseline interferometry. Interferometry is when you observe with two distinct elements and combine the signals. Oftentimes, they're physically close enough that you can just pull a cable between them and record the data simultaneously. Obviously, in our case, from the North Pole to the South Pole, pulling a cable isn't an option. But there is this technique of recording the data simultaneously on a distant source, and then using supercomputers to combine and correlate them after the fact, that preserves all the principles of interferometry. And the nicest thing about this is it gets you the spatial resolution that you would have gotten as if your telescope was as large as the separation between the telescopes. So your resolving elements are basically the distance between any two pairs of telescopes. Here is the black hole that we are imaging. Hopefully it's a very nice night, devoid of moisture, that kills the millimeter wavelength observations, unfortunately. So clear night, and because we are observing in the millimeter wavelength, or 230 gigahertz, we need to record the data at that rate. And not only record it, but time tag it, so that after the fact, when we're combining the signals from different telescopes, you can match up, multiply them really, but match up wavelength by wavelength, and pretend you've combined the signals as if it's a normal interferometer. For that reason, we use hydrogen maser clocks to time tag at the rate of 230 billion times a second the incoming wavefronts. Okay, a little bit more about interferometry, because it's going to play a lot into what we can and cannot do with EHD data. So when you have an interferometer, let's say that you had two telescopes shown here and here, and you took one instance of an object in the sky. That's going to give you one spatial frequency. It's like hearing one note of a song, right? So it's going to give you an information that is the separation between the telescopes projected onto the sky, divided by the wavelength of the observations. And of course, it's going to be symmetric in this quadrant and this quadrant. You can't make an image from one point in Fourier space. That's one spatial frequency. So what do? We rely on the rotation of the Earth in order to fill in the components of the Fourier space, different projections. And of course, as more and more telescopes come into view of the source, as the Earth rotates, then you jump to different telescope combinations that fill in different separations and projections. So ultimately, you fill in more regions. Each one of these tracks is a telescope pair. Some are close, some are far away. This is our largest separation, which is 8 gigalambda. In units of lambda, 8 billion lambda. And that's between Hawaii and Iram in Europe. So great. So now we have something to work with, but still, this is what would be called a very sparse coverage in the interferometric plane. Or in interferometry lingo, it's very often called the UV plane, the UNV being the horizontal and vertical components of your frequencies. Okay, so what do we do to go from here to an image is going to be one of the themes of this talk. Any questions so far on the technique on EHD? If not, let me introduce you to the two sources whose images I already showed you in my cover slide, M87 and Sagittarius A star, the two close by supermassive black holes, Sagittarius A star, of course, being the closest, being in our own galaxy, and M87 is close as well. So why are we working with these two targets and not some other black holes? This dates back to some of the work that I have done actually as a graduate student back in 2000, identifying the best sources in the sky that we can target for imaging, and not just for imaging, but with the express goal of getting down to what is called the black hole event horizon. That point of no return where you expect light and energy to fall into the black hole and imprint a particular signature on the image that would tell you, yes, that's a black hole. It would look very different than a star. It would look very different than a galaxy. So if you wanted to resolve the event horizon, you would need a couple of things. One, you would need the angular resolution to get down to the separation that is required. Two, black holes themselves don't emit light. The only reason why they are bright or observable to begin with, because their strong gravity pulls matter, gas, dust, whatever, from nearby stars into an accretion flow that circles around the black hole and makes its way down to the event horizon, that point of no return. And during that process, the gas heats up and emits light, typically through synchrotron radiation in the wavelengths that we are interested in. So you need light, you need an accreting black hole, you need it to be big enough so that you resolve the event horizon. And the third thing you need is not too much light. Otherwise, your view is going to be obscured. It's going to look like a torus as opposed to just a source of light that illuminates the innermost region of the black hole and allows you to see that transition from light to no light, just like we saw in those pictures. So this was the work that we did back in 2000. This was in the millimeter wavelengths, the image size in units of Schwarzschild radius for Sagittarius A star, and at what frequency, these were the two existing observations at the time, and at what frequency do you hit the event horizon and you have the ability to resolve it. And that turned out to be 1 millimeter based on the theoretical models that I built at the time. And this was another investigation a year later, considering the possibility of doing this interferometry in the X-ray wavelengths, both identifying Sag star and M87 as the targets where we would have the highest resolvable size, basically the highest resolution, so the smallest resolvable size. And this was motivated by what was then called the Beyond Einstein program. There was an experiment proposed as part of it called MAXIM, a space interferometer between in X-rays, basically LISA, but not for gravitational waves, but X-rays. And my colleague Tiziana Di Matteo and I considered what would be our best targets if we wanted to image black holes in X-rays. So fast forward 20 years, of course, oh, sorry, I skipped one point here. If I can. Even then, even when we identified in 2000 the best targets for this experiment, the angular sizes are tiny. They are of order 50 microarc seconds. I know for astronomers in the room that makes sense. For non-astronomers, it will never make sense. It's like millionth of a degree, or that's why even with these optimal sources, what you end up needing is an Earth-sized telescope in order to achieve the resolution to get down to the horizon. And that's why we considered interferometers from the get-go. Single dish is never going to get there. Okay? All right. Sag star is towards Sagittarius. M87 you may not know as well, so let me introduce you to our second favorite source. It is in the Virgo cluster. between the arms of the Virgin, there is a galaxy cluster called Virgo for obvious reasons. M87 is not the biggest galaxy in that cluster, but it has the brightest jet source that's bright in the millimeter. And that's what alerted us to the possibility that there's a black hole there, an accreting black hole. And more studies over decades turned out to identify it as a good target. Okay, I'll show you what the data look like when we collect all of these interferometric, what are called visibilities. The Fourier components are referred to as visibilities. I already showed you this plot over here. This is for M87 during the 2017 observing campaign, which is still to date the most comprehensively analyzed data set of the EHT. We're working on subsequent years as we speak, but I already showed you this. Let's say that I'm, for a second, not interested in a two-dimensional image, but I collect all of this information simply based on separation. So forget the azimuthal information, collect it all as if it's just a separation between telescopes, and plot the Fourier amplitude as a function of baseline length in giga lambda. This is our spatial frequency, this is our amplitude, and color coded based on the telescope pairs. What do you see on the right? Well, something unmistakable that we saw was a ringing pattern. It starts high, there's a minimum, high, there's another minimum. Okay? A ringing pattern in a Fourier transform immediately tells you that you're dealing with a compact source, that it has a finite size. It could be a disk. It doesn't guarantee that it has that donut shape that you're looking for black hole images, but it tells you that you're dealing with something with a sharp edge, basically, a compact source. And this is a Bessel function, which, if you transform it, will give you your image. Okay. How about Sagittarius star? Same thing, color-coded, exactly the same. This is the resolution, highest resolution of the array. With Sagittarius star, the South Pole telescope can see it, M87 it can't, so it's a little bit different. Again, what do you see? Ringing structure. Okay, so even though our data are sparse, even though you can't just take what I've shown you, you can't just take this and uniquely invert it into an image, there are things that you can say uniquely. I have a compact source, it's of this size, and it probably is a disk or a ring. Okay? That you see without doing anything to the data. In fact, the first minimum in the visibility amplitude is what gives you your image size, just the basic property of a Bessel function. So just by staring at this, you can say my image diameter is of order 52 microarc seconds. Okay. After this, it's a lot of analysis, and I mean a lot of analysis. For example, one of the first things that we did, and I know there are people in the room who have worked on these imaging methods with interferometric data, is turn to regularized maximum likelihood methods. You take you take an image plane, you divide it up into a lot of pixels. Each one has a brightness that you're trying to determine. And this is your data, now not color-coded anymore, but I promise you it's the same M87 data. You can have a trial image. You can put a blob here, blob, whatever your trial image is. Take its Fourier transform and say, is this a good fit to the data? And here what we're showing are the horizontal and vertical cross sections. Those are the two separate ringings that you're seeing here. No, I think anybody with the naked eye could look at this and say, that is not a good fit to the data. Okay, so it will we'll keep changing it. The problem is you can count the number of pixels in this in this image. It's a lot. It's about 1,000 or more. You don't see 1,000 data points here, which means that you have to add a penalty that you don't have enough degrees of freedom to uniquely determine your image. So you have to make some assumptions about your image. You can penalize for rapid changes in brightness, which we do, so smoothness. You can penalize for total flux. So effectively, instead of defining a chi-squared, that's theta minus model over error squared, which is the chi-squared definition that we're used to from just normal fitting, with different weights, you can add penalty functions that are called regularizers, okay? At this stage, we used very generic image property, smoothness, positivity, et cetera, type of regularizers, and nothing about what we knew about black hole images. So if you do that and start basically changing pixel brightness and doing this chi-squared minimization, it will give you an ideal image. This is for M87. This is one of the possible images for one choice of regularizers that fits the data. Okay. Now you know that not only is 52 microarc seconds of order, and it's a compact source and it's ring-like, but you have a more particular brightness distribution. Is everything in this brightness distribution believable? The honest answer is no. It is very much dependent on what regularizers you assumed. By changing those, you can change where these bright spots appear. You can't change the size. Remember that you could see with naked eye. You can't change the thickness all that much as long as your penalty for smoothness over different pixels remains the same. And also because you don't have enough information to fill all of these pixels, we blur the final image to the EHD. Like we blur over the possibilities of all of these regularizers worse than the EHD resolution. And that's why you get a fuzzy donut as opposed to a Krispy Kreme. Image properties that you can see, M87 on the right, Sagittarius A star on the left. Overall, there is a hole. The Holy Land promised the shadow is, oh my God, I'm on a roll. Okay, I promise I won't do that again. There is a hole in the middle. There is a ring of brightness around it that comes from this synchrotron emission from the hot plasma falling onto the black hole. It's relatively narrow, meaning that if you did delta D over D, it's less than half. And in M87, there's a pretty pronounced north-south asymmetry that we attribute to the motion of the gas around the black hole that introduces a Doppler brightening. So in this particular case, the gas at the bottom is coming towards you, the gas at the top is receding from you. That gives you that Doppler boost difference. And in Sagittarius A star, for a variety of reasons, that north-south or east-west asymmetry is not as pronounced. And these bright spots in Sag A star are a little bit more pronounced. Again, primarily because of the artifacts of how the RML methods reconstruct sparse data. Okay. Why? Why do we arrive at these image elements is going to be the rest of the talk. So I'm going to go through, hopefully time permitting, 3 distinct parts. One is tell you about all the models and analysis tools that we built to understand the image properties, and not only that, but go from those image properties to here is what the property of the black hole causing that image is. Ultimately, we are after the gravitational tests that can be done with black hole images. In the second part of the talk, I want to briefly touch on where our models are insufficient, okay? I don't want to give the sense that this is a solved problem. Accretion flows around black holes are very, very challenging. So where are we not doing well? And in the third part of the talk, having learned all of these tools and models, can we actually do imaging better than what we did with RML? Okay, hopefully I'll get through, if not, some other time. So our bread and butter simulation tool for understanding how a gas behaves around a black hole is called General Relativistic Magnetohydrodynamic Modeling. General relativistic because the black hole space-time bends light and paths of matter, etc. So you need to formulate it in GR. Magneto because it's a plasma, so the magnetic fields are coupled to the motion of the plasma. They're generated and also affect the motion of the particles. And hydrodynamics because it's a fluid. Apologize, this is reading. Now we use this, I'll just show you an example, what this looks like. This is from one of the earliest models that we built of flows like the one around M87 and Sagittarius star. Low density, low emissivity, so basically low radiative efficiency if you are more familiar with that field. Gas is being fed from out here. It comes towards the black hole. This is showing magnetic energy and thermal energy. You can see that it is increasing towards the black hole. And these are very costly simulations, especially if you're trying to do it for different magnetic field geometries, like initial geometry. Just like in the sun, I mean, we have to explore the effect of the magnetic field. You want to explore different black hole spins, how the space-time affects the properties. For example, does it couple to how a jet forms from the flow? You want to explore those things, etc. And of course, there are also other parameters like where is the observer with respect to the black hole spin axis, right? Am I looking at it edge on or pole on? All of these things we try to simulate with these large suites. I'll just show you a couple more renderings because we ran a very large suite of new GRMHD simulations, both for, excuse me, M87 and for Sagittarius star as part of the EHT. We explored different magnetic field geometries. This is called SANE. That's basically a more tangled magnetic field. MAD is a magnetically arrested disk, different black hole spins. These are magnetic field lines. All I'm trying to show here is that the parameter space is large. There is a lot of theoretical understanding that we build by running these simulations and then trying to understand how observable properties couple to some of those intrinsic properties of either the flow or the black hole itself. There's a second step after we run these GRMHD. At that point, we are not treating the radiation as part of the modeling. After the fact, we do general relativistic radiative transfer. This is our image plane. These are our various pixels. And we ask, what determines the brightness of each pixel? Well, this ray originated from somewhere in the flow. And as it traveled towards the observer, it picked up contributions of different emission along the way, as long as it's optically thin, which these flows are at these wavelengths. And also you will notice that different paths are bent, different amounts, depending on how close they got to the black hole. So this part of actually taking GRMHD and rendering it, this time around, we did it on the Open Science Grid because it's a really nice application, along with many clusters. And we broke the record on the usage on the Open Science Grid. We actually, there was an article that said HT pushed it over any previous record. So pretty expensive, but really fun work to do. So this is not my friend. I'm letting you go. Okay. A little bit about what forms the shadow and what forms the properties of the image. So there are special radii around a black hole. I'm going to show it for a Schwarzschild black hole, meaning no spin. These are the photon paths. There's that event horizon that I already mentioned to you at 2 gravitational units, basically that scale with the mass of the black hole. And there's a photon orbit that turns out to be actually more important than the event horizon. That's the point at which a photon that is tangential can make infinite circles around the black hole and critically escape or critically fall in. Okay? Why is that important? Well, we're adding up contributions as we go of the emission around the black hole. So that could get really, really bright, right? So I will show it to you this way as you change the impact parameter, how you all of a sudden go from just a tiny little path length to a lot of circles around it. So if we now go here, you can see that different impact parameters, and especially this critical impact parameter that marks the boundary at 5 gravitational radii between photons falling in and photons that are deflected but do not fall in, could actually get pretty bright. One more rendition of this time allowing for the, or just showing the accretion flow. As I mentioned earlier, as you fall in, density increases, temperature increases, magnetic field strength increases. All of these things increase the emission that gas is able to produce. But it's not just the emission. The image brightness is going to be proportional to the path length over which you pick up that brightness, right? So they're optically thin. So this original idea of how many times you hit the disk is in discrete numbers is not correct for our sources. It's really how much integral you pick up as you go around. So if I'm at this impact parameter contributing to outer part of an image, I pick up this much, which is a large path length because my disk is h over r is about this big, right? But it's cooler and lower magnetic field, so I pick up a particular amount. Coming in, my path length is smaller, but it's brighter per little step. Now come to D. I have crossed the accretion flow once here. I've gone around picking up nothing. I've crossed it once here, and then I've crossed it again here. So that gives me a particular image brightness that effectively sets pattern that we see from not bright, or let me go on this side. Not bright, increasing brightness, very bright at that multiple path and its surroundings, and then it drops down. Why doesn't it drop down completely? Well, it's because there is still gas in front of me. So as I'm looking through it, I can still pick up a little bit of contribution. Okay? So the center is pretty dark, but that's what forms the image, and that's why we are looking for images of this type. So the simulation library that we built explored all of these characteristics: changing mass accretion rate, changing black hole spin, magnetic field geometry, electron temperature, Okay, you see that there are lots and lots of morphologies here. Some are crescents, some are rings, some are thinner rings, some are thicker rings, some have substructure, some don't. But this gives you a very large library to work with in order to understand what is the space-time property and what is the plasma property. None really have zero hole, but they have more opacity of stuff circling in front of them that obscures your vision. So none of them in the image itself lack a hole. It's just sometimes it's less reachable. And that's why that choice of 1.3 millimeter optimized for everything that we know about these black holes, optimized the Goldilocks. Enough light, but not too much light. If you're going to test general relativity by looking at these images and comparing them to what you theoretically expect, you better have alternatives that are outside of general relativity. Because you can't show, like the only thing you can show is this fits GR. But what if every other theory out there, and there are many, many extensions of GR, many alternatives to GR, and for a good reason, right? Cosmology has some problems explaining everything that we see within general relativity. And we have information paradoxes, we have unsolved problems with quantum mechanics. So it is extremely natural to look beyond GR for what is the complete theory. So we did that. In addition to the GR MHD models, we built, this was my pandemic project. It was super fun. It was like doing another PhD. Semi-analytic models, basically, of black holes that don't assume the Kerr metric as the metric of the black hole. And putting an analytic plasma model, a completely covariant analytic plasma model around it, obeying all conservation laws. So you still solve for energy, momentum, and mass conservation. And for different metrics, Kerr on the left, but JP metric, Kerr-Sen, boson stars, dilatons, wormholes. What does the image structure look like? Do I still get a ring? Do I still get a hole? And do I get the relationship between the two? What we found out is that you can actually change the size of the ring, no problem. You can change the size of the shadow by changing parameters that are, for example, adding a quadrupole that's not a Kerr quadrupole in GR. But they change proportionately to one another. So if you stretch one out, you stretch the other out. And that's a really, really good thing. I think that's on my next slide, because what we are measuring, the thing that we can see is the ring. We can measure the size of the ring, but the space-time properties are the shadow. That's embedded in where that sharp drop-off is in the photon orbit and then the horizon. So if I can't establish a relationship between the two, I can't use the ring size to do a GR test. Good news is that we were, through that entire library, as well as the non-GR models that we explored, we were able to establish that relationship.
Can you tell us what those circles are in this image? Is that 2 times the Schwarzschild radius of the photon orbit?
No, actually, this is all our feature extraction tools that we used in order to measure the ring size. We allowed for azimuthal variation. So these are the, I believe, if I remember correctly, 95 and 90% contours or 68% contours of what you would consider your image diameter to be.
So what would the photon orbit be on this scale?
It would be about 90% of where you're seeing these circles. The reason is that I will show you in a second, using this entire library, when we measured what is my ring size, ring diameter, over the shadow diameter, it peaks at 1.1. So about 10% less than what these rings are showing would be your shadow size. Here it is. It's this calibration factor. of the image diameter to the shadow diameter. In light of time, I will skip over these, how we measured shadow diameters for non-Kerr things, etc. But I'll show you the distribution. These are for all of those MAD morphologies. The blue contours are 95th percentile of the width of the ring and the fractional diameter difference. So when that's 0, the ring diameter and shadow diameter are on top of each other. But as you can see, it's not peaking at 0. It's peaking at 0.1. And here as well, it's peaking roughly around 0.1. But the good news is, whatever it is, it doesn't matter. It could have been 1, it could have been 1.2, it could have been 0.8 for all we care. You can quantify it. You can quantify the uncertainties in it, and then you can fold those uncertainties into the uncertainties in your GR parameters that you're trying to constrain. Same thing here. For now, I'm showing it as a histogram as opposed to a two-dimensional plot that has the width as well. These are the analytic Kerr and analytic non-Kerr. As you can see, that fractional diameter difference is peaking roughly at 0.1, but we quantified this and folded it into our measurements. I will skip this. This is what our imaging algorithms are doing to the image. So are we introducing biases and uncertainties by using particular imaging techniques on the data? That also got folded in as a second source of uncertainty, multiplying that alpha 1 that I was just showing you. So I measure something, I put it on the left. I have an expectation if it's a Schwarzschild black hole of a given mass on the rightmost. Those are all my calibration factors that I have to take into account between the space-time diameters and the image diameters. And delta is the allowed deviation from GR. If delta is 0, it's the GR prediction. With one caveat, this is the Schwarzschild diameter. Spin introduces a 3% correction, plus or minus 3%. So delta within a few percent of 0 is still within GR for a spinning black hole. Okay? And well, what do we know about the mass of the black hole? This is all for Sagittarius A star. And using the prior known mass and distance to Sag A star, using the orbits of stars that, Nobel Prize, I think a few years ago, that gave us an excellent measurement of the mass of the black hole. And as you can see, the fractional deviation is peaking around 0 with that band that is allowing for that unknown spin. And these are all our contours with different imaging techniques and different calibration factors that I just mentioned to you. Okay. Quickly, are the models adequate and complete? Well, the fact that we've run so many different scenarios and looked for similarities between them and looked at how they reproduce other known things about Sag A star and M87, like its broadband spectrum, like other observations that we've done over the last 20 years, they are doing really well. They are getting the steady state characteristics extremely well, because ultimately, all you're saying there is obeying the conservation laws. What happens to matter as it falls into a black hole? Yes, you may not know exactly what the field geometry is, exactly what temperature it reaches, but you can allow for enough variation in your models to capture those basic characteristics. One thing we could not do well is getting the variability right. So these are turbulent systems, right? It's not a static image. In all of those library models that I showed you, stuff was swirling around, flickering, flux tubes were going in and out of view. So what we are predicting is these 1.3 millimeter flux as a function of time in hours. That should do something like what you're seeing here. for two different simulations. This is the data. So we are overproducing the variability. Let me show it to you in one other way. This is the flux as measured by SMA and ALMA telescopes on the 4 different days of the observations that we're analyzing. And you can see the variation between these days is much smaller than the variability that we're predicting. Okay. With one caveat, here there is an actual flare. Black holes show flaring activity. For Sagittarius star, especially in the X-rays with the Chandra X-ray telescope, when we look at it for a while, we can see daily flares where it really brightens, probably magnetic reconnection events that we can't take into account in our simulations. So that's a really brightening event that's much, much, much larger than the flux excursions that I'm showing you there. So we can't reproduce the flaring, but we overproduce variability during quiescence. What's the reason for that? Well, we don't know, but if I were to guess, the culprit would be how we are treating the electron temperature. Let me show you on this scale what our problem is and what a possible solution is. The global simulations that I mentioned to you, this scale of an event horizon for a million or billion solar mass black hole, this is actually for Sagittarius star, so it's not even billion, is 10 to the 16 centimeters. The electron gyro radius at which dissipation processes happen, plasma processes inject energy into the electrons and heat them, is here, about 10 to the 2 centimeters. There is no simulation in the world, and there will never be a simulation in the world that can directly resolve kinetic processes, individual plasma instabilities or kinetic processes, while at the same time simulating things that are relevant at the global astrophysical scale. This is 14 orders of magnitude in separation. So we can't resolve the dissipation. What we do is solve for the whole plasma with as much resolution as we can, 3D, follow the ions, calculate ion temperature from energy conservation, and then say the electrons have a fraction, get through some channeling, separation, a fraction of the temperature that the ions are getting. This happens in the sun, like this 2 temperature plasma. There are many examples, and there are reasons to basically not think but show that this happens in low luminosity black hole accretion flows. Good news is that there are intermediate mechanisms or tools that we've been looking at, such as gyrokinetic simulations that allow us to analyze how energy flows. It's the typical turbulent cascade, but in the presence of a magnetic field through compressive and alphane cascades, how these waves are excited and what do they couple to. And you can do these simulations on a smaller scale as long as you're stirring your flow, like you're simulating stirring your flow at those large scales. And those are already giving us much more constrained, much more physically motivated, I want to say meaningful information about what this is happening. So this is a recent paper that just appeared from our group about the electron heating to the total heating that goes into ions and electrons as a function of the plasma beta, which shows magnetization in the flow, based on some of the earlier work of Kawazura et al. In 2020 of compressive and alphenic waves, as well as Coulomb collisions and compressive heating, a better handle on, depending on where you are in your flow, these are the GRMHD plasma betas, what your electron to ion temperature is likely to be. In this post-processing that I showed earlier, we allow for much larger variations just to be on the safe side, or, it's parametrized. This is a step towards, it's not the final answer, but it's a step towards more realistic plasma processes and electron heating that will hopefully get there. So all of this modeling work, I would summarize as GRMHD models get the main features right. They cannot capture and will not capture dissipative processes happening at the much smaller scales, but we have other tools that are able to give us more, like, higher fidelity, better physics-informed models, and they may be, it remains to be seen, but they may be able to fix the variability problem. I know you're probably running out of steam. One last little bit that I want to share with you is that actually all of this work results in us being able to make better images. And why is that? I showed you how to reconstruct sparse images by changing your regularizers. You make all of these different possibilities that we have to take into account as, maybe this is the right answer because we don't know how to fill in these gaps. And it creates some artifacts, as you can see, and it blurs the image to a resolution that is worse than the EHT array resolution. So this is what ends up happening for Sagittarius star. What if we machine learned from these extremely large suite of simulations that are physics motivated? The physics of image formation is very well understood, and we have about 30,000 images to learn from with very, very different morphologies. And knowing that we're dealing with a compact image, what if we use these to inform simply a basis in order to reconstruct our images? So the goal is to fill in the missing information, but to do it in an efficient way, so a compact set that we can use. So for that, we opted to do the dictionary learning based on PCA just because it's linear, it's orthogonal, it's efficient. So take all of those and find its principal components simply to build a basis. It's not agnostic, but it's also fairly complete because you can reconstruct anything that's out, pretty much any compact image that is outside of your training set as well. So you do that, you take an example snapshot, you filter it to the EHT resolution, you say, how many components can I use to build it? That's pretty good. What if I use 20? That's even better. That is now at the signal to noise of the EHT resolutions. And of course, if I added more components, then I would be able to get more and more of those features. We settled on 20 because of the current EHT signal to noise. And that's a very small number of components to use to reconstruct images. Now, it worked. It gave us a much better image of M87 that I will share with you in a second. But I want to explain to you why it works before I show it to you, because everybody's reaction is you baked it in. You trained it on known images, so clearly you baked in features that you may or may not be there. That's not the case. The reason is that for a compact image, remember that Bessel function ringing? There are many different ways that ringing can happen, but the wavelength of the ringing is directly proportional to the image size. So if I have enough image morphologies to learn from that has many different types of ringing with the right correlation lengths, basically what I'm saying is I might have only these tracks in this part of the Fourier space, but really that nails down pretty much anything that can happen in this blue circle that is 2 gigalambda in radius, about 2.5 gigalambda in radius. So if I told you what you're looking for is a sine wave light, and you have a few high signal to noise points, you will be able to draw that sine wave, right? Because once you know what that wavelength is, there are very few things you can do to that sine wave. Bessel functions are the same. The minute you say I have a compact image and this is the ringing pattern, you can change the amplitude as much as you want, and that's the completeness of your set. But there isn't much you can do. So if I have this track, I'm filling in 2.5 gigalambda of information. So yes, the HT array is sparse, but the particular characteristics of our image are allowing us to make a high fidelity, faithful reconstruction that is not overfitting, and that doesn't require the blurring that the RML methods required at the native EHD resolution. Here, there is nothing that makes up information in the sense that there is nothing beyond 8 gigalambda that the native resolution of the array wouldn't have seen. It's simply what the array could have seen. Okay, so machine learning and this theoretical work allows us to utilize the full resolution of the array, and sharper images, hopefully, in the future will lead to better physics constraints. I don't have that to show to you because this is brand new work from just a couple months ago. So I will leave you with Sarjay Star and a skinnier M87 image. Thank you.
Yeah, what's the range of wavelengths or frequencies, because this is in the submillimeter, that for which this technique will work? And is there any way you could improve the spatial or the angular resolution by going to shorter wavelengths?
Yes, thank you for asking that. The next steps of the EHD collaboration, one of the major directions, is doing these observations not only at 230 gigahertz, but at 345 gigahertz, which changes the angular resolution. And it also gives you an additional piece of information about the plasma. Gravity won't care about the frequency, but synchrotron emission sure will. So what is underlying, what is on top of its questions can be, and improved resolution can be addressed by going to 345. Our observations earlier this year, the observing campaigns happen end of March, early April timeframe because of weather. And several telescopes already tested their 345 gigahertz. Not every telescope has the dual frequency instruments on it yet, but as we're building up that capability in the array, we already did a test run, and I'm really hopeful about those results.
Okay, so first of all, great talk. Thank you. And I'd like to kind of leap off what Sebastian asked you was, so the resolution is basically naively lambda over the baseline.
Sure.
Why not just increase the baseline? I've read some discussions of, well, we already have the Earth, but what about if you put a satellite, in low Earth orbit, or potentially even people would love to have a telescope on the moon. Is that really feasible?
It is a very active area of research, and one that I'm very interested in. It is not feasible today, and I'll tell you why. So you have two options. One is you go to the low Earth orbit. You have telescopes that are orbiting every 90 minutes, which means you can fill this in no time at all. You have just a few telescopes in space, maybe laser comms between them, or maybe you downlink the data, and you fill all of this. But as you know, low Earth orbit, what do you want? Like 500 kilometers above the Earth's surface? It won't bring out the highest resolution element compared to Earth-size array. The low Earth orbit added to the Earth's diameter is nothing. So you could go that route. The second route is put telescopes in, for example, a third of the distance to the moon. And I say a third of the distance because we've done this study in 2012 and identified at least 15 other black holes that you could resolve the event horizons for. So bringing those just 2 in our prime target list to at least 15 by increasing this. But then you will have different filling factor for your UV. What is the problem? The problem is that we are recording every wavefront and time tagging it, which means about a petabyte of data per night of observing for about 10 stations. We can't downlink that. So my group is working on, first of all, this optimization between what is better science-wise. Do we learn more from a better coverage at low Earth orbit, or more black holes at higher orbits, GEO and above? Second, how do we deal with the data problem? How much number crunching can we do in a power efficient way on board? Do we correlate on orbit versus downlink? What do we downlink? So we are exploring a lot of different, it's a very exciting next decade type of development, but I don't have the answer yet.
Well, thank you.
I'm aware of basically a lot of work being done regarding quantum information in things like space-time conditions, like black boundaries and black holes are one of them. I'm curious, basically, I'm wondering, what lacking seems to be a lot of those experimental conflicts. You have theories and ideas to try to tease out maybe what might be going on in conditions, but like, how can you see these models and simulations and images that you're producing here move us closer towards experimental backing for any of these ideas?
That's a very good question, and that is very much the motivation behind this work that we have done, going beyond Kerr, going beyond GR alternatives, and saying, where do we start to see differences? What is it that we're looking for? Are we looking for a change in shape? Are we looking for a change in size? Are we looking for different features that appear? So a big motivation behind this was trying to understand, if I change the space-time, whether this is quantum gravity, or wormhole, or not even a black hole, a boson star, can I tell the difference between these possibilities? And for certain scenarios, the telltale sign is the size. It's rarely the shape, although there are some circumstances in which you deviate from circularity. So that could be a measure. But you can change the size, and if it was one of these somewhat more extreme cases, we would have been able to tell with the HT already. But with sharper images and potentially even more sources in the far future, we will be able to get down those constraints to a level where we say, I can rule out this type of quantum correction, maybe, but not that type.
Thank you so much for a great talk.
Thank you.
For M87 star, we know it's an actively accreting black hole. We can observe the jet. We can safely assume that the image that we get is the light that's coming from the accretion disk. And that way we can infer blue shifting and red shifting, we can infer the spin rotation, we can infer black hole mass.
Sure.
For Sag A star, it's not an actively feeding black hole. And the timescale variability is what, hours or minutes to hours, something like that for Sag A star. So it's not a disk, it's just whatever we were able to capture of any gas that's moving around it that's illuminating. So we can't, I'm just making sure, because I've asked a couple of times, we can't infer things like the spin direction of a disk or the spin axis of black hole Sag A star, because it's not the same structure as M87 star, right?
So it is true that there are very large differences between M87 and Sag A star, but one correction, it is actively accreting. It's just that it's accreting at a mass accretion rate that is even smaller compared to what is capable of. So what is capable of, we try to quantify it with a number called the Eddington mass accretion rate. for what it's worth. It's spherically symmetric, etc., but it is a number. Sagittarius star accretes about 2 orders of magnitude below M87's mass accretion rate in units of m dot Eddington. But it is accreting. It is very much being fed by stars in the vicinity. There are S stars, there are further stars. So there is angular momentum gas coming in and forming, as far as we can tell, an accretion flow around Sagittarius star. What are the differences? It's 4 million solar masses as opposed to M87 6 billion. So M87 ate more efficiently, grew more efficiently. M87 has a jet, Sagittarius star doesn't, but its broadband spectrum is very much like M87's broadband spectrum. When you go all the way from long wavelength radio to X-rays in both, you see that. And when you look at, for example, when you look with Chandra, you see the flaring activity that is pretty typical of accreting black holes. So it is accreting. It is low radiative efficiency, just like M87. But there are differences, which actually makes me happy that 2 different black holes of different masses, potentially different spins, that we know nothing about. And one with a jet, one not, their images end up looking really similar because, hey, gravity for the win, right? I mean, if it was so dependent, let's just go back here. If it was so dependent on the particulars of the accretion processes, plasma processes, then maybe we wouldn't have been able to obtain the same image structure in both. Does that help?
Yeah. Well, so real quick, can we infer anything about the spin axis of Sagittarius star from that image alone, or is there not enough information?
There isn't enough information. All we can say is accounting for the spin uncertainty and the observer's inclination uncertainty with respect to that spin or angular momentum axis, we are within the band that GR predicts for size. That's all we can say right now.
Thank you very much.
Yeah, thank you. Yeah, question from the chat from Mike Renshaw. What is the hope of resolving the shadow of a black hole in a high Newton rate above 1% AGN?
Little, for 2 reasons. One is when you bring up the mass accretion rate to such a high level, you form what is called an optically thick, geometrically thin disk. Exactly the opposite of this. These are geometrically thick, optically thin. AGN disks are geometrically thin, optically thick. So you would need to see some sort of light being reflected from the innermost part of that accretion disk. And that experiment you would have to do in UV. There is no millimeter emission or any radio infrared type of emission that is coming from the innermost parts of those AGN type disks. So you would have to change the wavelength and make a UV interferometer, which is pretty challenging. The second thing is they're not as nearby as some of these more dormant types of black holes. So you would also have to go out further in distance, increasing the angular resolution challenge. That's why our black holes look so different than Interstellar, the movie black holes. There's that thin accretion disk like coming in the middle, and it's the image characteristics are different. You would potentially, like in the 70s, there were some early calculations for optically thick disks if you went to UV.
Yeah, thank you. Yeah, now a question from me.
Okay. Different hats? Okay.
Yes. So you showed the GRMHD simulations. So with black hole, I'm wondering how those are driven, meaning that what are the boundary conditions which actually causing all this variability? Is it just the turbulence which is naturally developing in the uniform flow, or there is something else at the boundary?
That's a very good question. Thank you. It's at least partially turbulence. We feed these simulations typically from a torus that is in the outer part of the simulation domain. So it's initially in pressure equilibrium, and then we let it start trickling down and then form an MRI-driven turbulence and then reach steady state. But of course, even in steady state, there is turbulence. So no matter what, there is going to be some variability that comes simply from that turbulence that is causing density and magnetic field perturbations. But it's not just that. It is also how we then take that information and paint electron temperatures on top of that, which we don't calculate from first principles, as I was explaining. I think we introduce some artifacts in our prescription of, we try to be physically motivated, but it's a prescription. And I think in that electron temperature prescription, we're introducing the artifacts that you're seeing in that, like, why is it so variable? Saturday star isn't that variable type of thing. It's a guess. I mean, I'm not saying we've definitively shown how much of it is turbulence and how much of it is whatever else that we're getting right or wrong in the simulations, but that's my guess.
So basically, if I can ask a follow-up question, you think that the electrons have some sort of the, I don't know, the inertia with respect to the heating, and they take some time to heat up and to build, which smoothes out your variability picture, right?
Absolutely. That's a very good way of describing it. Yeah. As opposed to the plasma beta change, let me instantaneously change the electron temperature as a prescription. That's not, it can't happen.
It seems that there's still some open question regarding the variability.
Yeah, variability is an open question. Better models of this, what we want to build as subgrid physics of like the kinetic properties in the plasma, open questions. There's definitely more to do, but I just want to be able to distinguish, yeah, we learned a lot from these models and they're getting these characteristics right, and these are open questions as much as possible. Yeah.
Any more questions?
Is the center of the torus visible at all angles?
At these mass accretion rates, yes. What changes is going from a more crescent-like image, if you're looking at it edge on, to a more circular-looking image, more ring-like image, if you're looking at it down the pole. Another way to make that symmetry, which we see in Sagittarius star, is the flow, because of magnetic support, can become sub-Keplerian. What that means is that gas, instead of rotating in the phi velocity with its Keplerian, like full Keplerian orbits, it can actually rotate more slowly. Its phi component of the velocity can be less, which would reduce the image, like this brightness contrast in the upper and lower parts of the thing. So it's always visible. It can be a disk or crescent, oh, sorry, not disk. It can be a ring or crescent, but it doesn't have to be always a ring here, always a crescent there. That's the most complete answer that I can give you.
Hello, great talk. So I'm actually doing pretty similar work on BE star disks, where I'm taking interferometry data and then creating a physics-based model and trying to match it. And so in BE star disks, my research is showing that there's generally like spiral features in the disks that aren't really been modeled that much before.
Yeah.
And generally they have like a global oscillation model where it's kind of like a yin-yang symbol, where one side is just more denser than the other. Have you seen that in your accretion disk models?
Not quite yin and yang type, but certainly you will see in some of these where, especially the thicker disks, some density waves forming, like these. So that type of brightness ripples or density ripples forming in the disk, yes, we see it, but not really like one hemisphere versus the other.
Have the models been making, like, trying to approach that, or is this just directly from the images?
This is directly from whatever that initial condition and parameter combination resulted in for that GRMHD simulation, and then we turned it into a set of like time series of images that, if you could resolve it, it would look like this.
Okay.
Am I getting your question right?
Yeah, so you're not like hard coding in like a spiral feature. You're just
No.
like, Okay.
No, it develops on its own. Whatever turbulence and thickness, etc., develops, it develops on its own.
Any more questions? So take the previous last question. So is Einstein still correct?
Sadly, yes. I mean, we're not going to let it go. I think there are very interesting different problems that are happening also in cosmology that make us consider if we have all of it right, and as well as the disparity with quantum mechanics. So I'm hopeful that there are going to be some signs of something beyond GR appearing somewhere, but neither what we have done so far with our uncertainties, nor what the gravitational waves have done so far within their uncertainties is able to uncover that, if they are there. And if it is the ultimate geometric theory of gravity, then we'll have to get creative about how to solve all of those paradoxes. And
you haven't saturated all the information ETH are bringing us, right? Or do you think is there more information you can squeeze off from ETH?
So we have the observing campaigns from 2018 onwards. We're working on publishing those right now. The pandemic year we couldn't observe. There was another year we couldn't observe, but still, the 345 gigahertz might tell us something. Like we haven't looked at those data, and increasing the resolution maybe, like, and then in the far future maybe. But there is nothing that I know that I haven't shared with you, if that's what you're asking.
Thank you very much.